Hello, and welcome back. In this video, we're starting section 13.6 for real. If you haven't done so yet, it's a good idea to go and watch these videos I made about basic curves in 2 dimensions, because these are going to be our key to understanding surfaces in 3 dimensions. In section 13.6, we're specifically talking about cylinders and quadric surfaces. So these are 2 different kinds of surfaces, 2 different general families of surfaces. So like I said, our key to understanding these things is similar to how in those videos I made of the basic curves in 2 dimensions, how we found y-intercepts and different intercepts. We set x equal to certain constants or y equal to certain constants and then solved the equation out and found, in that case, we found points, intercepts. In the case of 3 dimensions, we're going to be setting variables equal to constants, and what we'll get out are curves rather than points. So what do we call these things? We call these traces. So a trace of a surface in 3 dimensions is just the set of points where the surface intersects a plane. And you get this by setting, one way to get traces, specifically traces that are parallel to coordinate planes, are by setting variables equal to constants. So in this video, I'm gonna focus on 3 basic traces and then a little bit of generalizations of those. So an xy trace, so this is, what does the surface look like if you intersect it with the xy plane? What's the curve that comes out of that? We can do a yz trace, which is look at the yz plane and look at how the surface intersects that. And finally, the xz trace, what does the surface look like when we intersect it with the xz plane? And so this is the idea. One way to think about these are if we're sort of standing parallel to one of the planes, what is the surface going to look like? That's a way to think about this. So to kick this video off, traces, I'm going to be playing around in our e-textbook with a couple examples in there. So I'm going to go ahead and jump to that. There we go. So here we have a figure. We'll learn the name of this figure later. It's not important right now. I just want to show you sort of how traces work. So right now I have no traces on, but what I'm going to do is I'm going to turn on, let's do the xy trace first. So before I turn it on, I want you to think, what does this surface look like when I intersect it with the xy plane? So when z is equal to 0, what does the surface look like? One way to think about this is looking at it from above. Well, it doesn't quite do it justice because of this. The figure is getting all blown up. I'm going to go ahead and reset this thing. It's getting a little bit out of control. Oh, come on. Sorry, everybody. I'm going to reload the page. All right, that's a little bit better. What does the surface look like when we look at it? It almost looks rectangular. That's not quite the idea. What do we have there? Let's show the trace. XY trace. There we go. That's a little bit better of a picture. So the XY plane is now pictured as this sort of light gray, and the green line is the intersection of the surface with that plane. And as we can see, it's an ellipse. So when we set z equal to 0 in the equation of this surface, which we'll do later on in an example, we should see an ellipse. All right, so that's the xy trace. By the way, we can also do traces that are parallel to the xy plane. So that'll be setting z equal to various constants. We'll talk a little bit more about that later. But this isn't the only trace we want to do parallel to the xy plane. We can also do xz plane. So think about the xz plane. Here's the x-axis and the z-axis. So the xz plane would be the one I'm facing right here. And let's take a look at what that looks like when I intersect it. Again, make a prediction. What do you think it's going to look like? What sort of curve is going to come out? To me, it looks like it's going to be a parabola. Let's take a look. I'm going to turn on the xz trace. And what do you know? It certainly looks like a parabola. It could be hyperbolic. It could be some other kind of curve. It could be a catenary curve. So the only way to really know for sure is to work out the algebra, and we'll get to that later. But it certainly looks parabolic. In fact, it is parabolic. And then finally, we'll do the yz trace. So y-axis, z-axis, that's going to be this plane here. Let me turn that one on. And again, we get another parabola. So notice how this is a nice way of understanding this surface by looking at these 3 traces. So looking at it from above or below, we get ellipses. If we intersect it with the xy plane, we get an ellipse. And then the yz and the xz, we get parabolas. One's a little bit wider than the other. but regardless, we get parabolas. So that's one way to understand this surface. All right, I'm going to work through one other example. Hopefully it'll cooperate a little bit better. Here is another surface in 3 dimensions. And again, we're going to compute traces. So I'm going to do the xy trace first. So that is xy trace. So the xy plane itself is when z is equal to 0. So in general, we get sort of slices parallel to the xy plane by setting z equal to just any particular constant. So z equal 0, that's the xy plane. Z equal 1 would be the plane z equals 1, to be a little bit higher up. Let me turn on just the xy trace. There's the xy trace. It's an ellipse. Cool. And so this is what I mean is I can change what I'm setting z equal to. Here I'm setting it equal to 0 and I get this curve. If I set it equal to -1, it's going to move that plane down a little bit. I'm going to get another ellipse in this case, but you see it's moved down. I can set z equal to -2. It's moved down yet further, and it's an ellipse. And if I kept going down, if I kept setting z to bigger and negative values, eventually I'll keep getting ellipses like this. If you can imagine that, keep getting ellipses. Eventually I'll get down to just a point, and then I won't have an intersection at all. So that's also possible, is no intersection. I could set z equal to positive quantities, 1 or 2, and you can see the plane moving up. Right? I can keep moving up if I want, and I'll keep getting smaller and smaller ellipses until eventually these curves will vanish. Let's just see how that looks. Keep going. Now it's z is equal to 4.5. Let's see, can I go any further? Will it let me? No, but okay. But if you can imagine z equal to 5 would just be this point right there. So you can get points out of this. Point is sort of a degenerate curve. Or you could get nothing out. So if I take like z equal to 7, it won't intersect the surface at all. All right, well, to better understand this, we need to take planes that are not just parallel to the xy plane. What if we took planes that are parallel to the xz plane? That's going to come from setting y equal to constants. So setting y equal to 0 gives us just the xz trace. And as you can see, we get an ellipse. And then I can change my y value. That's going to move it backward or forward across the y-axis. So setting y equal to 1, I get a trace that looks like that. Again, an ellipse. And we can keep moving forward. Eventually, if I keep moving this, I'll get ellipses, 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 a point, and then nothing. So we're understanding this surface by looking at slices. And the big thing here is that there's sort of 3 kind of dimensions in which to take slices, right? 3 sort of varieties of parallel planes. And so I can change y there. Let's take a look at setting x equal to some constant. So that will be, if I set x equal to 0, that'll be the yz plane. So that'll be one, perpendicular to this plane, and just yz like that. Let's take a look at that one. So setting x equal to 0 gives us an ellipse again. I can pull it back or move it forward, and I'll keep getting ellipses, right? So it's moving back into the figure. I can pull it forward by setting x equal to a higher positive 1. I get another ellipse. Maybe that one's almost circular. Nah, it's still an ellipse. And so we can see, at least with this surface, that if I take any traces that are parallel to one of the 3 coordinate planes, I end up with ellipses. And that's why we call this figure an ellipsoid, because it's ellipses sort of in every possible trace. Let's maybe do one more of these. This is called a hyperboloid of one sheet. We'll talk about these later. Right now, again, I just want to understand the traces and seeing how this is different from the previous figure. So let's do, how about xy traces? So just the xy trace would be the xy plane. That just disappeared. Sometimes I need to get rid of some of those. Not cooperating super well. Let's see. I'm going to turn on the xy plane, the xy trace. So that's setting z equal to 0. You see here, I have z equal to 0. I get an ellipse. I can move it up. I get ellipses. I can move it up again. I get ellipses. I can move it down. You can see I'm going to get ellipses still. So it looks like all of the traces that are parallel to the xy plane generate ellipses. Now think about what kind of curve are we going to get if I intersect with, say, the yz plane or the xz plane. What does this outline of this surface look like? One way to think about these traces is it's sort of the outline of this figure. What are those? Do you recognize them? Did you watch the videos before this one? Maybe, maybe not. Those are both hyperbolas. So let's just turn on x equal to some constant. So these are going to be traces parallel to the YZ plane. And yeah, look, we get hyperbolas. So that is when we set x equal to a constant, x equal to 0 in this case, we should get a hyperbola that generates this curve. I can pull it back. I get a hyperbola, albeit a little bit different of a hyperbola. I can pull it back even farther. And now I get, it's having a tough time dealing with this. I've pushed it maybe a little bit too far. Well, you'll actually get our two intersecting lines. And that's sort of a degenerate hyperbola. It's not quite a hyperbola. It's kind of a degenerate version of it, is two intersecting lines. So let's see. How about turn on XZ traces. The XZ trace itself, we get a hyperbola. I can pull it back. I get other hyperbolas. I can move it forward along the x-axis. Oh, sorry, this is along the y-axis. Sorry, these are XZ traces. I can't remember if I said that wrong. But these are traces that are parallel to the XZ plane. And I get hyperbolas here as well. So it looks like when viewed from above or below, I get ellipses. So those are XY trace is an ellipse, and then YZ and XZ traces, these are hyperbolas. So sort of in two dimensions, cross sections, we get hyperbolas, and then in the other dimension of cross section, we get ellipses. And that's how we can recognize that this is a hyperboloid of one sheet. So we'll encounter, all these ones I've showed you, these are examples of quadric surfaces, which we'll talk about in a later video, but this idea of traces is our key to understanding them. So we're going to get into the algebra of this. Like I said, it looks like a hyperbola. How do we actually verify it is a hyperbola? Well, that comes from setting, in this case, y equal to 2 in the equation. We'll get an equation of just two variables, x and z, and we'll see that turns out a hyperbola. So that's the idea. We'll get a little bit more detailed in a later video. All right, thanks for sticking around. That is it for this one.